This recording is one of the recordings in the series of lectures covering neurophysiology, and specifically we're going to look at the generation of an action potential. We've previously discussed resting potential, then we talked about graded potentials. Now we're going to discuss action potentials. Now action potentials, or we call nerve impulses, this is a means by which neurons communicate. In order to generate that action potential, we have to disrupt that membrane potential. We have to have enough of a depolarizing stimulus to reach something called the threshold. And that's going to be initiated here at the axon hillock, and it will then travel down that axon. Now, one of the things to kind of remember is that action potentials are a little bit different than graded potentials. So over here on the left, these are examples of graded potentials. They were ones that we'd had depolarization that takes place. So remember, graded potentials, the magnitude of the change is directly related to the strength of the stimulus. So you see a greater response with a higher stimulus. However, with an action potential, once you have a stimulus that is enough to reach threshold, which is going to be minus 55 millivolts, I need to get that membrane potential to minus 55 millivolts in order to generate an action potential. What you'll notice, though, that from this one to this one, I had a greater stimulus, but that action potential looks identical, because action potentials are all or none. The size of the action potential will always be the same no matter what the strength of the stimulus is. If it's enough to reach threshold, once it reaches threshold, the action potential either is going to say it's going to occur. So either it occurs or it doesn't. And so they always are going to look the same. Now, the way that our bodies, our way we're going to be able to interpret information differently is because since action potentials all look the same, is how frequently they're generated. That's how we're going to say we can encode information. Oh, that is someone's pressing on my hand a little bit stronger. And so it's actually by frequency of action potentials, not by the magnitude of the action potentials. So what we're going to do is we're going to go through the steps involved in an action potential. So, quick reminder, you have a lot more sodium outside the cell. You have a lot more potassium inside the cell. Those two cations, it's important to know those because they're going to be major players when we talk about action potentials. At rest, the resting potential is minus 70 millivolts. And that means you're negatively charged inside by minus 70 millivolts compared to the outside. We have a lot more negative charges inside versus outside. Certain channels that we need to be aware of is what you have here. This is a ligand-gated sodium channel. It's closed under resting conditions. Something needs to be bound to it in order for it to open, but it's closed. You have right here and right here, those are voltage-gated sodium channels. At resting conditions, what you're going to notice is these activation gates, which are on the extracellular fluid side. Those activation gates are also referred to as, so you know, they're actually also referred to as M gates. Those are closed. On the inside, the intracellular fluid side, you have these inactivation gates. They're open. They're also referred to as H gates. That's another term for them. So at rest, the activation gates are closed, the inactivation gates are open. Both of those gates need to be open for sodium to move across. That activation gate's closed, you'll see sodium's not allowed to come in. Okay. You also see another player that we'll be talking about is a voltage-gated potassium channel. At rest, that activation gate is closed under that potassium channel. So potassium is not moving through that particular channel under resting conditions. So when we start, we're going to start, we got that resting membrane potential is minus 70 millivolts, okay? We have an unequal distribution of charges across that membrane. So what we're going to do is look at the first step. So actually, before we look at the first step, this is my analogy, is I think of those voltage-gated sodium channels as having a door, like a storm door and a regular door. So we're inside the house. This is the inactivation gate. This is the activation gate. That's closed. The inactivation gate is open. No one's moving across because one of the doors is shut. Okay, so we're starting at resting membrane potential. What do you notice that just happened? Look at here. That sodium channel is now open. So what will happen if this sodium channel has now been opened? You have all that sodium outside of the cell. It's going to want to go in. So I'm actually going to just draw it this way. Here's the sodium wanting to come into the cell. Two reasons. It wants to go from its high concentration to low, plus it's also attracted to all these negative charges here. So there's a favorable electrochemical gradient which allows sodium to move in. We're going to see depolarization. You're going to see a reduction in membrane potential. And so what you're going to see is what you see with that light blue. Okay? So that light blue is what you're going to notice. Okay? So we got this. So there's some depolarization. Now, if we're going to change this to minus 55. If enough of those channels are open, we'll reach a threshold stimulus. If not, you'll just have, once that stimulus is removed, we'll go back to membrane potential. It would just be a graded potential. But we're going to say we had enough of those sodium channels that opened up, enough sodium moved in. We had the membrane potential go to minus 55 millivolts. That's the magic number. I want you to think of the voltage-gated sodium channels to being like on a spring-loaded mechanism. So once a certain number of doors open, we reach threshold, all of these voltage-gated sodium channels will pop open. And so once that happens, all these voltage-gated sodium channels open, and so the floodgates are open. And so you're going to have a mass movement of sodium into the cell, and you get enough of that sodium going in the cell, we're going to actually end up getting to a positive value. And so what's happened is, at threshold, the activation gates have opened. That, because this is a voltage-gated channel, these gates are sensitive to what the membrane voltage is. In this case, the activation gates will pop open if you reach that minus 55 millivolts. So sodium is going to flood into the cell. And so, again, you got so much sodium coming in, look, it even became a positive number. Now, once you're starting to get to this membrane potential, what's going to happen is the sodium channels are going to inactivate themselves by closing this inactivation gate, which you see right here. It's like a plug. So sodium can no longer move across that membrane. At the same time, when you get to that membrane potential, the voltage-gated potassium channels will open. So that's the magic around getting the right number, where these gates open up on the voltage-gated potassium channel. So what's going to happen? So we're no longer having sodium move across. You've now opened up potassium channels. What's going to happen is potassium is going to want to leave the cell. And actually what I'm going to bring your attention to the next picture. I'll come right back. So come back here. Oh, I'm going to draw this different. I'm going to actually change this because I thought I changed it. Here, these should be like this. because now this is positive and out here should be negative, okay? And so what's going to happen? Potassium is going to want to leave the cell. You're going to lose positive charges, and it wants to leave the cell 2 reasons. It wants to go down its concentration gradient from high to low. Plus, again, it's more attracted to where they have more of the negative charges, which now are going to be out here versus inside the cell. And so what we're going to see is repolarization. So here's demonstrating, you're looking at the house from outside. Here is the inactivation gate, the one closer to inside the house is closed. So that sodium no longer moves across, but the voltage gated potassium channel is open. And you see here, we have repolarization that's going to happen as a result of that. So losing those positive charges, we're going to start to get back to where we're supposed to be. Now these channels, these gates, are a little bit slower to close. So what's going to happen, as you see here in the purple, you have a brief period right here of hyperpolarization. So because those voltage-gated sodium channels are a little bit slower to close, it's going to go a little bit more negative than the -70, but at some point it's going to go back to resting. Now what's going to happen is while we're doing this, as we're repolarizing, is when the voltage becomes low enough, the inactivation gates of those voltage-gated sodium channels will reopen and the activation gates will close. We're going to get back to where we started with those voltage-gated sodium channels, and at the point where those activation gates of the voltage-gated potassium channels close, you're no longer going to see that potassium moving across. So what's happened is, here's your membrane potential, resting potential. We had some depolarization because we've opened up, say, a ligand-gated sodium channel. You reach threshold, so the activation gates of voltage-gated sodium channels opened up. You see this depolarization, this upstroke in the action potential. This point here, those sodium channels are now inactive because the inactivation gate has closed. Voltage-gated potassium channels open, so we have repolarization here. You do have a brief period of hyperpolarization, but at some point we're going to get back to here. Now the thing is, what we did is we had started with all this sodium here and the potassium here. Because of what you saw going on right in here, now we have a lot of the sodium here and we have the potassium out. We need to get back to where we started. And so this is why the sodium potassium pump is important. We're gonna show you it right here. This is showing it there. So let's go through the steps again so you can see. So at resting potential, you're negative inside compared to the outside. You have more sodium outside, more potassium inside. You depolarize, you see the sodium ions moving in to the cell. You get enough of those positive charges coming in, you're going to see it become positive inside. During repolarization, potassium is leaving the cell. We're getting back to that negative number. Now we want to get back to that resting potential. You want to have that distribution the way it's supposed to be again, is you have the sodium potassium pump. Sodium potassium pump is going to pump out 3 sodiums in exchange for 2 potassiums. So let's look at it here. So sodium potassium pump is an active transporter, primary active transporter. It pumps 3 sodiums out of the cell in exchange for 2 potassiums to go in the cell. So you end up with that unequal distribution of sodium and potassium across that membrane. You stimulate that cell again, we're going to have another action potential, okay? But we're going to talk about some things that are part of what you see here. So here's again all those steps, but there are parts during what you'll observe where if I apply a stimulus to that membrane again, I will not generate an action potential, or I'd have to have a higher than normal stimulus. So that's going to come into the next lecture. So here we're just looking at the steps involved in the generation of the action potential. So we had to disrupt that memory potential. We had to, in this case, depolarize it. We opened up some ligand-gated sodium channels. Enough of them opened up. You reach threshold potential, which right here, we're going to say it's minus 55 millivolts. You started your action potential. Whole bunch of sodium moved into the cell through those voltage-gated sodium channels. At that point, both the activation and inactivation gates are open. You got depolarization. Once you start getting up in here, those sodium channels will now become inactivated. Voltage-gated potassium channels open, so potassium is going to leave the cell, and we're going to repolarize. They take a little longer to close, so we have a brief period of hyperpolarization, which is number 5. When you're starting getting down in here, those voltage-gated sodium channels are going to reset to where they were at the beginning. So at where you see at the resting potential, which is number 1, the inactivation gates are open, the activation gates are closed. So in order for sodium to move across those voltage-gated channels, both the gates need to be open. So that's key. Both of them need to be open. So we're going to stop here. Next recording, we're going to start with this picture, and we're going to talk about something called refractory periods.